All right, settle down and get your seats. So my name is Janet Vertesi. I'm at Princeton University. I'm delighted to welcome you today to the panel on Mars exploration. The planet Mars has fascinated astronomers and space scientists for generations, to say nothing of historians, and this particular sociologist as well. And the papers in this session are focusing on the red planet, but they each display very different approaches to the history of Mars exploration. And each of these approaches reveals some of the contingencies and temporalities of this exploration work. We'll hear first from Richard Zurek, who's the chief scientist for the Mars program at JPL. Focusing on the missions, Zurek will take us through the trajectory of Mars exploration and its understanding from Percival Lowell to Curiosity. Such an approach will show us how each successive mission builds upon the successes and critical questions of the prior mission and how our knowledge of Mars is built up over time. Next, we'll hear from David Grinspoon, curator of astrobiology at the Denver Museum for Nature and Science. David will take the science point of view, specifically looking at the growth and change of the astrobiology community and its questions throughout this period of Mars exploration. And this kind of approach can tell us more about the concept of habitability, how it has been historically understood, and with what kinds of implications for the kind of science that is done. JPL historian Eric Conway focuses more on the engineering side, specifically engineering for a single mission, the much belabored Mars sample return. And those of you at the meeting in Germany earlier this year will know that that is a topic very dear to my heart as well. In this way, Eric Conway will definitely show us how a group of engineers at JPL were on the front lines of trying to implement shifting declarations from Complex, from the Space Science Board, and even the president himself, which reveals the complexities on the ground of being caught in the middle of 30 years of NASA crossfire. Finally, Henry Lambright, professor of public administration and international affairs and political science at the University of Syracuse, will take an individual approach. Focusing on the role and contributions of different NASA administrators, Lambright reveals the importance of leadership, complexities of decision-making, and the critical role of individuals in pushing forward the vision of Mars exploration. As a final note, before we begin, as an ethnographer working with contemporary planetary exploration missions, these four histories continue to resonate throughout space exploration today. And the past is very much with us in the present. This is not just as a form of curiosity, no pun intended, but as the past moments of budget crises and bold visions show us, the concerns of our predecessors are very much our concerns today. And there are lessons here for how they chose to resolve those questions that can help us to address our own historical moment and our challenges. But perhaps more profoundly, their choices shaped in a foundational way the kinds of spacecraft we fly and the kinds of science that we do today. And that's one of the things that brings work on Earth and work on Mars ever closer together and continues to inspire our enthusiasm for Mars exploration today. So with that, I'd like to start by welcoming Richard Zurek to the podium. Chief Scientist for the Mars program at the Jet Propulsion Laboratory. Dr. Zurek's PhD is in the atmospheric sciences. He specializes in the atmospheres of Earth and Mars. He served as project scientist for Mars Surveyor 1998 missions, Mars Climate Orbiter, and Mars Polar Lander. He's worked with data from Mariner and from Viking, has led atmospheric advisory groups to support aerobraking engineering for our current generation of Mars orbiters, and is presently the project scientist for the Extraordinary Mars Reconnaissance Orbiter.
Well, what I hope to do today is to trace through space exploration, but also before that, the persistent themes that have made us interested in Mars, and to show you that in many ways those themes still drive us today as to what we want to do at the Red Planet. However, our concept of what Mars is and what it may be has certainly changed over that time. So just very briefly, if I go to the first slide here, here's what I'll try to talk about, those persistent themes. And I'll start going back to what I'll call the Percival Lowell view of Mars. And then we'll talk about the two waves of Mars exploration. You've already heard about the lost decade, which is what separates that first wave, where we flew by, we went into orbit, and then with Viking we landed. And then in the second wave of exploration, we've got more of an orbiter-lander synergy and added a new element that you heard about earlier too, which is mobility on the surface. And we'll talk about how that has helped advance what we do at the planet. Ending up with an idea about what Mars is today, but also I need to caution you that that story is very much unfolding at this very moment. We have two orbiters plus the Mars Express European orbiter active at the planet. We still have the Opportunity rover working on the surface, and of course Curiosity has now arrived to join them with its own expedition of things. So, to begin, those dominant themes. Mars is a place that we think has changed enormously over time, that it was very different in its early history, and it is now a different planet than it was in that early time. The geologic evolution of the planet has certainly changed. Over its history, giant volcanoes have built up. There are places in erosion on the planet. In some places, the wind has acted for 1 billion years in a way that we don't really have any terrestrial analog for. So there are processes, and this is what the planets give us, are these natural laboratories to be able to understand processes. But of course, a key thing with Mars has always been whether or not life is on the planet today, or it had been in the past, whether or not there is evidence of that past life that might be preserved today. And that's certainly something that we've been looking for in our space exploration of Mars. So let's begin, well, not really from the beginning, but at least let's go back 100 years, and let's talk about what the view of Mars was then on those 3 themes. Percival Lowell thought that he had a simple explanation for what Mars was. It fit all of the observational data that he had at hand, and he was responsible for accumulating more information about the red planet in a more systematic way. In fact, he coined the term planetology in a way that was actually a great debate at the time, because he was accused of being very selective about what things he took from geological studies of the Earth about how the Earth had evolved and such. And that's because his simple idea is that Mars was just an older version of the Earth. Mars and Earth have many similarities. They rotate about the same period, so their days are about the same. The temperature contrast between night and day are moderated because of that. Rotation axis of both planets are tipped over about 25 degrees. That means there are seasons. It's a warm summer pole and a cold winter pole on the planet there. So those similarities, plus the fact that Mars was all land, and in fact about the same land area as the land area of the Earth, and the fact that both had atmospheres in which the sunlight went to the surface and could power not only the atmospheric circulation, but would be available as energy to life forms on the surface. Now, there was something exceptional about Mars in Lowell's view, and that was the canals. He and other observers saw the canals. They saw them in different forms. Some were very large and fuzzy markings on the planet that they drew. Others were, as Lowell drew them, were very straight and geometric that were indicating that, hey, there's more than just life on the planet. There's actually intelligent life on the planet. We've come a long way from that time, but even if you go to the mid-century here, that is into the 60s, when Mariner 4 was being launched and we were about to embark upon our space exploration, it is amazing how strong those ideas were and how we continue to debate them. In fact, there was a Mars handbook that was published by NASA in the late 60s, 70 cents, by the way, a real bargain for a student at the time. That handbook still wouldn't dismiss the possibility of canals, even though Mariner 4 had already taken its pictures and they were still being analyzed. The resolution of those pictures was not quite adequate to completely rule out what might still be on the surface of Mars. And in fact, our space exploration can be thought of as a desire to go to ever higher spatial resolutions to be able to see the fine detail that could actually help us test key theories about the planet. So this was Percival Lowell's view of the planet, and it had polar caps. Mars had polar caps. It had dark areas. One argument that the dark areas could only be explained by life was the fact that they changed color with the seasons. And in fact, they even reappeared after dust storms had brightened those areas, and the areas got dark again. And what else except vegetation would be able to do that? So trying to understand those kinds of mysteries has also been about what we're about. Now, by the 60s, the Earth-based measurements were also getting better, and there were some signs that Mars wasn't nearly as hospitable an environment for life as Percival Lowell had thought many decades earlier. The atmosphere was getting thinner. Well, our idea of the atmosphere was that it was not nearly as thick as we had thought it had been. And there were also better techniques in the imagery and the photographic photographs that were taken through telescopes and such that called into question the very idea that the canals existed. Mariner 4 successfully launches. I might remind you that Mariner 3 was the first attempt in the same launch opportunity. The shroud didn't separate. It went into the ocean. They figured out the problem. They diagnosed it. They fixed it. Mariner 4 was launched in the same launch opportunity. We're talking about a period of several weeks here. I doubt we could get the failure review board together in these days to respond in such a way. And that was a sign of the experimentation of the times, the risk they were willing to take, and just the excitement and the drive of getting things done. Okay, so that first wave of space exploration, Mariner 4, Mariner 6 and 7, flybys. We're just seeing bits of the planet. Mariner 4, the images went across 1% of the planet at fairly coarse resolution, over 100 kilometers per pixel in most cases. Mariner 9, first spacecraft from Earth to go into orbit around another planet, and that showed us a very different kind of Mars, and I'll come back to that. And then it's succeeded by the Viking experiment, very ambitious, as you heard this morning, in which we were saying there's a paradigm that if life can exist anywhere on the planet, it exists everywhere on the planet. So that I can land, I can scoop up some soil, I don't need to be very particular about where I land, and I should be able to find out whether or not the planet has life. What did we find? Well, Mariner 4 showed us this, a very moon-like landscape on the planet. We shouldn't have been too surprised. In fact, papers have been written that we should expect craters on Mars. It was closer to the asteroid belt after all. The impact rate should be higher than for the moon, but we still had this mind of a thicker atmosphere that was screening out some of those impacts, making it less so. It was certainly a rugged planet, and as we got more examples of what it looked like, we still could see things that were saying, yes, it's not just a dead world. There are polar caps, for instance. And there are things like you see this ring feature in the middle of the lower right thing there, which those are clouds, and they could be orographically derived. Percival Lowell hadn't seen any mountains, either at the terminators or when they were seen on edge. And mountains would have been a bad thing for his canals, because canals would have to go up and over such things, and they didn't seem to do that in any particular way. But in reality, of course, there were some rather tall mountains on Mars. The great volcanoes that we've seen, that's the Viking image over there that shows you what we were indeed looking at when we saw these clouds around the rings. We didn't appreciate just how high these mountains might be. In fact, there were several people, Bruce Murray actually, in a debate prior to Mariner 9 going into orbit, said there are no mountains on Mars. Geologically, it doesn't seem to be a very active planet. And of course, Mariner 9 disproved that in a big way. But first, there was a global dust storm, similar to this one that was shown later in these Hubble images of the planet. And when Mariner 9 went into orbit, it couldn't see most of the surface except for 4 prominent dark spots, which turned out to be the summits of these very tall volcanoes rising high into the atmosphere. Well, Mariner 9 showed us not only had there been water active on the planet, but there must have been episodes of massive water activity. Streamlined islands in some of the big channels, massive canyons that were cut, and there are stream beds inside the canyons that have shown the changing positions. Furthermore, it showed that, for instance, in the polar caps were layered in a way that suggested ice ages and the progressive buildup and maybe tear down of these things. And that, of course, excited us about what the planet might have done in recent geologic time. If you needed more evidence that water had flowed on the surface, there were these valley networks. However, they weren't everywhere, and it suggested that there was a kind of episodic nature to the climate change on Mars. Well, all of that was good. The fact there was water was still on the planet. It hadn't completely desiccated, even though it might be much drier today than it had been in the past. When Viking went and landed on the surface, though, we were disappointed in that when we scooped up pieces of the soil, put it into the astrobiological instruments that were on Viking, we didn't get definitive evidence that there were any life forms. In fact, we couldn't find carbon in the material, which was strange in itself because there should have been inorganic carbon just from the infall of meteorites on the planet. So that suggested that the surface, in fact, could be a very hostile. There could be oxidizing agents that would break down the very compounds that were important to life as we knew it. Well, that gave us pause. A bigger pause was the fact that we changed the launch system for the human program again. And so we had our lost decade, and then we got back to exploration of Mars. There were some stumbles in doing that, but once we did, what we found, we got maps of the surface at resolutions that were unprecedented to all of planetary exploration. We also were able to do things like actually measure the topography, just how high was everything. Did those channels actually flow downstream, downhill? And we were able to do that. For a time, we actually had a better global topography map of Mars than we did for some regions of the Earth. Other things that we were finding was the presence of ice in the mid-latitudes, close to the surface. So one of the questions is, if Mars had all this water early, where did it go today? One thought was it had been lost to space. In fact, that was Percival Lowell's idea about planets just gradually lost water over time. The Earth would do that too. It was just behind Mars in that planetary evolution, because Mars, being smaller, was an older planet in his scheme. What we know now is that the other place that water can go and still be there to interact with the surface is in the near surface areas and stuff. So, evidence for past water activity on the ground and in the near surface. Phoenix dug down through a few centimeters of soil, exposed the ice. We know it is there. It's physically present. And we also found other things in the minerals that suggested there were reactions in chemistry that could go on that might explain some of those puzzling Viking results 2 decades earlier. So here's the litany of these spacecraft. And I'll point out again this idea about, in this case, there was a synergy between orbiters and landers. Viking actually pioneered it. The orbiters carried the landers into orbit, tried to find and scout out the landing sites for them. They didn't have much time to do that. And then the landers were released and went down to the surface. Well, now we do it by separate missions for the landers and for the orbiters, but they're still doing the same roles. Find the landing sites, find the interesting places on the planet, so that when we do land, we invest our time and effort in the right places, the places with the highest scientific potential. We also use the orbiters as relay communication satellites, which enormously increases the amount of data that we can return from the landers. And we're doing that at unprecedented levels today with Curiosity, and that's good, because if you count the number of cameras that mission has, they're quite a number. So, back to Mars, we started, and we introduced a new element, which was rovers, and the ability to move about the surface. That's important for 2 reasons. The biggest one is that you don't want to have the frustration of seeing something interesting that's just beyond the reach of your robotic arm or whatever device you have that gets your instruments onto the surface or picks up soil samples from the surface to ingest into onboard laboratories. So that mobility was very important. I think Opportunity landing in Eagle Crater, that was very pronounced, because there it was, the exposed bedrock, right there in that small crater wall, and if it had been a fixed lander, it would never have been able to sample any of that. Of course, it was able to see that, and let me jump ahead here, and one of the things it saw were these blueberries that you heard about, which were hematite concretions. Hematite is a mineral that requires the presence of water to form. This was the first of several lines of evidence that said this area had seen the activity and presence of water, in fact, in repeated episodes as well. Still early in the planet's history, and how early was hard to determine from these alone. Let me back up for just a moment here to remind you about these global topography sets. Not only did we map out the topography of the planet, but the magnetic fields. Mars lost its magnetic field very early, but the fact that there are areas that are permanently magnetized even today says it must have been a very strong field, and the loss of that may be very much connected to the loss of some of that atmosphere that was there in early times. We also see evidence geologically. Whenever you see layers, that's a geologist's dream, because that's telling you here's a rock record of history that I can read. We also saw things like these gullies on the walls of craters and canyons, and that suggests that maybe the planet is still active even today. We answered one of those old mysteries about how things darken, because on Mars, it's the wind that does it, but just not any wind. Sometimes there are the dust devils. And you think, dust devils, a track or two across here? Well, in some cases, you get thousands of dust devils creating a cross. And then from space or from the Earth, what you're seeing is the gradual darkening of this vast region, all due to the action at a very local scale. Seasonally dependent, you bet. You don't get those kinds of things until the surface is hot enough to get that vertical motion and the spinning action of the dust devil. Opportunity is still looking, ground truthing things today. We see some more spherules here, but these aren't hematite. These are something different, which just goes to show that everything is not the same everywhere on this planet. We thought that for a time, that it would be very homogeneous. The wind sort of carries everything around, but it's a very thin veneer that the wind is distributing over the planet, and getting beneath that and seeing what the planet is made of is what has helped us understand its history. Polygonal ground, you bet there was ice in this ground at one time. Maybe it's still there, maybe it's not, maybe this is now desiccated. But look at the scale of this, it's very fractal. You go from the A to the B, you go down to something that's a football-sized field, and we actually see that there's even patterned grounds within that at the resolution of a few meters. That's what resolution can do for you. Well, we're in a new site now, Gale Crater, that was picked on the basis of this reconnaissance of the whole planet, finding the right sites to try to go to look for some place that could have been habitable. That is, the conditions could have been conducive to life. Now, whether or not they were, that's what we're trying to get to, down on the ground, and trying to understand whether or not the role of water that we think we interpret from space is actually one that occurred. But there are indeed layers, and they are exposed here, and they're not just, it isn't just the morphology of these, it's also the chemistry of these. Some of these are sulfates, some of these are clays. They're stratified, they're separated in time, suggesting that Mars' history has had different water environments over that time. And our question is, how global, how regional was that? So what are the lessons to take away? Mars is a complex planet. It has many different kinds of landforms. It has a cryosphere, it has the land, it has the surface layers, it has an active atmosphere. It also is a planet that is changing today. These are called regional slope lineae, which is our way of trying not to say we think they're brine flows on the planet. Because what you see is these darkening things occur only during certain seasons. In fact, when the ground is the warmest, and a brine flow might be liquidized at that time and affecting on the place. Polar caps, they still change. In fact, we see a trend in which the South Pole cap may actually completely lose its CO2 cover in 100 years if that's not reversed by the natural processes. Sand dunes, we've now got a record long enough and with resolution key enough that we are able to see it actually moves. And of course, the big dust storms. Now, I want to just take a moment to address this question of novelty that was brought up. You know, major discoveries, right. Is there water in the atmosphere or not? That's kind of the stage we're at in many cases, certainly with exoplanets. You know, water in those atmospheres today. When you go to the next step, it isn't that you lose interest. The nature of the question changes, but it can be just as important. Take Earth as an example. We know there's ozone in the atmosphere. We know it changes, but we want to know why it changes. And because it's the Earth, we want to know whether or not we've got some part in that. The level of question gets more detailed, but the importance of the question is just as great as before. And in fact, we're still trying to get to that point of understanding whether there's life on the planet. All right. If I came back and wrote down, as I did here, why Mars today? Many of those questions are very much the same as what we saw before. No, we're not expecting intelligent beings. We're not expecting engineers to greet us, the engineers that built the canal system, because it's not there. But there is life. And there was a point made earlier about, yes, but if it's not a skeleton, if it's not people-like, is the public going to still be engaged in that? And I think what we've seen in the build-up to Curiosity says, you bet they are, because any kind of life form elsewhere, anywhere else besides Earth, is important for them. So the question that I'll leave you with is, will there be a third wave of Mars exploration involving humans and robots in different ways that we've done it before? To this point, the humans have all been back here on Earth, but still operating the vehicles far away. That may change with this third wave. Thank you. there are sort of two things that characterize the dark areas. One is they don't have dust, because that's the bright areas. And what makes a dark area dark and keep it dark, it tends to be a rougher surface, and you can think of many reasons for that. Some of the darkest areas on the planet, Syrtis Major, which is the most prominent of those, there's a huge volcanic complex, and that may be younger geologically, and that roughness is still there. And it's the roughness that actually stirs up the wind, which helps remove the dust after one of these global dust storms puts dust down and makes it brighter. So it is a combination of slope, roughness of the surface, and composition, in some cases, of the material.
Jason Callahan, you mentioned that the magnetosphere of Mars had dissipated early in its life, and that this might have resulted in the loss of the atmosphere, or parts of the atmosphere anyhow. What are the current theories on the cause of the dissipation of the magnetosphere?
It's a good question. One of the areas that we don't know very well is the interior processes of Mars. Fortunately, the Discovery program has just selected a mission that's going to put a seismometer down on the surface, put a heat flow experiment into the crust, which will help tell us about the models of that. One of the things I also didn't mention here is Mars has a dichotomy in its topography. The southern highlands, over which Mariner 4, 6, and 7 flew by, got most of their photographs, is a heavily cratered, high-altitude area. The northern areas, the northern plains, are relatively low in elevation and relatively smooth, looking like they've had a lot of debris that covers up that more cratered surface. All of those things could be related to the internal processes of mantle convection, plumes, hot spots, and then we also have the whole issue of the Tharsis volcanoes, those three giant volcanoes on the ridge in Olympus Mons, the solar system's biggest. How that develops. Was there a persistent hot spot? Think of Hawaii, where the islands aren't strung out, but they're all sitting in, that plume is just not moving. There's not much evidence of plate tectonics on Mars, and that seems to be one of the big differences in understanding its difference in the geologic evolution.
Yeah, just a quick comment on the dust and darkening and changes of albedo. In the telescopic days, the wave of darkening was always one of the stronger pieces of observational evidence. It did occur that might have been related to biological activity. And I've always found it interesting historically that Carl Sagan was one of the lead scientists in debunking the organic or plant life model for that in favor of moving dust around. He really followed the scientific method.
Exactly. The wave of darkening was the observation that there seemed to be this darkening of these features that occurred each spring, and it started, this wave of darkening started in the polar regions and seemed to sweep down into the lower latitudes. So, vegetation, wouldn't it be responding to spring just like it does on the Earth? And Jim Pollock and Carl Sagan picked up an idea that had actually been promulgated to say, well, the dark areas are really volcanic dust, and that's what's blowing around and changing with time. But they took it and showed that you didn't need a volcano to do that. And also, you could match the timing. The circulation would be that way to make it look like you were spreading the wave of darkening from the poles.
I apologize for a very provocative question, but I'm still asking you. Well, we have SNC meteorites on the Earth, just studied in detail in the labs, which are going to be confidently coming from Mars. Then why we need to undertake sample return mission? Do you think we will take something new?
The meteorites are an interesting set of samples. And the problem is we don't know their origins from the places on Mars. Where did that material come from? In fact, there's a whole cluster of many of them that are of similar age. So we're not getting a representative sample of all of the surface of Mars. So by knowing where we're going and taking those samples in the geologic context that we will observe when we collect them within these global data sets, that's the big difference. And that's the reason people have also suggested that we might just go to the moons of Mars and pick up material that has been blasted off of the surface. But that has the same problem. We don't know the provenance of those materials.
Our next speaker is David Grinspoon, who studies planetary evolution with a focus on habitability. David was previously at the Denver Museum of Nature and Science until yesterday, when he moved to Washington, D.C., to take up the first ever chairship of astrobiology at the Library of Congress. He's also the author of the award-winning book, Lonely Planets: The Natural Philosophy of Alien Life.
All right, thanks a lot, Janet, and thank you so much to the organizers for the ability to participate in this exciting anniversary party. I don't have slides, as Janet mentioned. I just yesterday finished driving across the country, and I don't know where any of my stuff or any of my materials are. But fortunately, this is a topic I've been thinking about for most of my life. So hopefully it's in here, and I do have some crib notes here. So the topic is evolving concepts of planetary habitability in the age of planetary exploration. And when I wrote the abstract, it wasn't actually specifically about Mars, but I've been shoehorned into a Mars session here, which is fine. I'm a big fan of Mars. And so I don't know if that means I should speak more about Mars or more about, or less about Mars, because a little bit of what I want to do is put Mars in the larger context of our thoughts about habitability. At any rate, the story begins, I think, between 4.5 and 4.6 billion years ago, when the Earth and its brethren and sistren accreted through a series of increasingly violent collisions, perhaps culminating with the moon-forming collision on the Earth. And then there were a smattering of waves of accretion that had quickly settled down and were pretty much all over by 4 billion years ago, setting the stage. And then things sort of bubbled and percolated and evolved along after that accretion. And then, perhaps somewhat mysteriously, about 50 years ago, something very strange started happening, a curious anti-accretion. And I mean curious in two senses of the word: curious, strange, and curious also because it was it was an event of an action of curiosity. Bits of the Earth started flinging back into the solar system from whence they had come. Small metallic objects filled with instruments orbiting back out into the solar system, heading for the other planets. Now, from the beginning, one of the motivating forces of this anti-accretion, this returning of some of the Earth back out into the solar system, has been the question of life elsewhere. As living beings and as a biosphere, we want to know, are we singular in some way, or are we commonplace? And even, in a sense, we are curious about curiosity itself. Is our quest, our ability to wonder about the rest of the universe extraordinary, or is it somehow inevitable, or both? Now, right now I'm hurtling through my 53rd orbit. So I'm just slightly older than planetary exploration. I have to confess I don't have direct memories of Mariner 2 from when I was 3 years old, but I do actually think I remember the Mariner 4 results being talked about in 1965. I definitely remember being excited about the appearance of the new Beatles record, Beatles 65, in 1965. And certainly, like all space scientists of my generation, the Apollo project launched me personally into space and set me on my current course. I, like many of you, I was also a science fiction freak from an early age, and as we gained the ability to send real machines into space, the excitement of participating in that enterprise eclipsed even the excitement of the fantasy space travels of Isaac Asimov and Arthur C. Clarke, although they all sort of merged together in my young imagination. At any rate, this golden anniversary that we're celebrating now provides an interesting opportunity to look back at our changing ideas about the limits of life and about the environments and natural history of planets and how they've changed throughout as a direct result of and during the time of planetary exploration. Planetary science as a field was born in response to planetary exploration and the need to forge a new multidisciplinary discipline that could handle this new data about the planets. It wasn't really a question about astronomy as traditionally practiced, in order to understand the planets, we needed the techniques and the insights of the earth sciences. So planetary science, in a sense, was born of a marriage between astronomy and earth sciences that was needed to scientifically respond to the opportunity to do planetary exploration. And just as another sort of personal observation in regards to that, when I went to grad school in the 1980s at Arizona, in a department of planetary science, none of my professors there had PhDs in planetary science, because when they were in grad school, there was no such thing. Now those same departments are filled with faculty that have degrees in planetary science. Similarly, the birth of astrobiology in the late 90s was sort of a marriage of convenience of planetary science with astrophysics as well, and biology, because we needed that approach, that combination of disciplines to deal with our growing sense that we were on the trail of life and our growing conviction that not only was that the motivation for planetary exploration, but we could now admit that it was the motivation for planetary exploration. Exobiology, of course, has existed since the beginning of planetary exploration, but it was a little bit more fringy, and NASA shied away from completely embracing it as the raison d'etre of planetary exploration until the late 90s, when some scientific developments happened which increased our confidence that this was really a worthwhile and solid endeavor, and that the public excitement about and the public support engendered from embracing the search for life was greater than the negative impact that was felt previously of the sort of ridicule factor that in some ways was the legacy of the Lowellian stain that took a while to erase. And I think that the birth of astrobiology was in response, can almost be boiled down to a response to 4 developments. And in my notes, the 4 developments are simply outlined as the Mars rock, Galileo at Europa, extremophiles, and exoplanets. And I could explicate those further, but given that we don't have that much time and that I think you all know what I'm talking about, perhaps I won't. But at least 2 of those developments, the Mars rock, of course, ALH 84001, and the discovery of very good, compelling evidence for an ocean on Europa, a likely or certainly potential, perhaps likely habitat on Europa, both of those were direct results of planetary exploration. And the extremophiles and the exoplanets are a little bit less directly related to planetary exploration per se, but certainly important in the founding of astrobiology as a field that's central to NASA's mission. Astrobiology is fundamentally about the relationship between planets and life. And so in thinking back over these 50 years and wondering where we're going, it's interesting to note that I believe actually, in a certain sense, our ideas about life have actually changed very little over these 50 years. And it's our knowledge of planets that has changed a lot. And I'll be a little bit more specific what I mean about that in a second. One of the things I love to do is read outdated books of popular science written by scientists and see what they knew or what they thought they knew and compare it to what we know or what we think we know now. One of my favorite writers in this genre is George Gamow. I have a copy of a book he wrote called Biography of the Earth, that came out in 1947, and its cover price is 35 cents, which gives you, little context on what else has changed in these decades. And it's stunning when you read that book, both what they knew and what they didn't know compared to now. For instance, they had had the insight that the Earth is very old and that you could determine that through radiometric dating. However, the age of the Earth is confidently given in Gamlov's book as 2 billion years old. So they had the principle right, but they didn't quite have the decay constants and the math right. The origin of the moon, of course, you know, the moon had broken off from the Earth and the Pacific Ring of Fire and all that, like we were taught in grade school. And there was no plate tectonics, but there is a section in that book about essentially exobiology. He does speculate on finding life on the other planets. And remember, this is 1947, and what he says is basically, he doesn't use this exact phrase, but what he says is follow the water. And so, in that sense, our basic idea about how to look for life hasn't changed all that much. Well, in 1953, the structure of DNA was deciphered, and at that point, I will submit to you, we knew as much about life as we know now. Not really in the details. If you're a microbiologist, you're sitting here getting mad at me. But what I mean is, we had the fundamental knowledge that we use now to look for life elsewhere. We knew that life was water in organics. And that's the sophistication of what we bring with us as we search for habitable environments elsewhere. So what's really changed is what we've learned about planets. At the dawn of the space age, both Venus and Mars were regarded by many scientists as pretty good habitats for life. As Rich Zurek outlined, there were some doubts at the beginning of Mars exploration, but the idea that could be plant life on Mars was still taken seriously, and the idea that Venus might be a watery world, there were some cracks in that view because of radio astronomy, but when our first missions left for the planets, it was still there was still a lot of optimism. And in fact, in 1959, Miller and Urey of the famous Miller-Urey experiment wrote an article in Science magazine talking about that it's quite possible that we will find DNA-based life on Venus and Mars and what we could learn from that. And of course, there's that famous paper in '61 that Carl Sagan wrote on the eve of Venus exploration talking about summarizing current thought about Venus, saying that it may be a carboniferous swamp, a windswept desert, a planetary oil field, or a global seltzer ocean. And that's a classic paper if you haven't read it, Science, 1961, Carl Sagan. But certainly, it wasn't outlandish. There could be life, our kind of life, on the surface of either of those planets. So the early results of the first interplanetary probes were very disappointing in that regard. Our naive optimism, perhaps naive optimism, was dashed by those first results about learning how alien those planets really were. New York Times editorial in February 1963, commenting on the results of Mariner 2, that was entitled, "Venus Says No." And it talked about, this marks the end of the beginning of mankind's great romantic dreams, and said, quote, "Mars now remains our only hope of turning this universal dream into reality." Well, 2.5 years later, the New York Times had an editorial commenting on the Mariner 4 results in July 1965, and that editorial was simply called "The Dead Planet." So there's a lot of disappointment at first in response to perhaps our naive optimism. Both neighboring planets turned out to be a lot less Earth-like in terms of surface environments that had been imagined by those planetary astronomers who inferred oceans on Venus and seasonal plant life on Mars. But optimism and wishful thinking reign supreme in this field, and they will not be dissuaded by data. Life was pushed off the surface of Venus and Mars and into the past of Venus and Mars. But in the subsurface of Mars, and maybe even in the clouds of Venus, and certainly in the glorious past, life still remains on those planets. For both Venus and Mars, we actually have reason to believe that each started out much more Earth-like, and there was a fall from grace. At least this is the story we tell ourselves and think we can support with evidence. So I have a list of 6 stages in our views of habitability in at least in our solar system. 1, naive optimism. 2, initial disappointment. 3, resurgent optimism, visions of past life, resilient life, which is really what Viking was based on, and non-surface life. Now, Viking was motivated by and perhaps helped to quash this wave of resurgent optimism. But also we've had evolving ideas about the habitable zone. And the habitable zone, which was actually really first discussed quantitatively by Su-Shu Huang in the early 60s, has become much more sophisticated now, and we realize it's not just a function of stellar distance, it's also a function of planetary evolution and size. If you swapped Mars and Venus, they might both be habitable. Mars's problem is not necessarily that it's too far from the sun, but it's too small. It's lost its activity and its atmosphere. So if you swap Mars and Venus, we might have 3 habitable planets. So, and then finally, of course, beyond the inner solar system, right, Heidi? We've learned a lot that's changed our ideas about habitability. And then finally, the exoplanet revolution. Let's see, how much do I have? Okay, 5 minutes. So during these same decades, our knowledge of Earth and the evolution and diversity of terrestrial life was also rapidly changing due to developments such as plate tectonics, which was in the early 60s still kind of a radical idea. By the end of the 60s, widely accepted as our unifying view of terrestrial evolution. And the plate tectonics led to the birth of Earth system science, which I think now we're trying to generalize to planetary system science. And a couple ideas that I think are worth mentioning are the formulation and debate of the Gaia hypothesis, as checkered a career of the Gaia, as the Gaia hypothesis has, and as much abused as it has been. I think it also represents an essential insight about life that's very important as we think about the relationship between life and planets potentially elsewhere. That is, the biosphere is an integral part of the Earth, the inseparability of the living and, quote, non-living parts of the Earth, and life is something that, in a sense, happens to a planet, not just something that happens on a planet. And a related idea that I have advanced that I'll just plug here for a second is something I call the living worlds hypothesis, which draws attention to the fact that life on Earth enjoys the benefits of residing at the intersection of 2 great heat engines, the internal one and the external one, both of which are very active. And I have suggested that for the long-term existence of a biosphere, this may be as important as simply the presence of liquid water. And the only other place we know in our solar system that shares that attribute, perhaps, is Titan. There was the, of course, the Chicxulub impact that really brought home to us a relationship between evolution of life on Earth and the rest of the solar system. It wasn't just an abstract concept. The rare earth hypothesis, which I regard as fundamentally wrong-headed, I have a paragraph here which I won't take the time to read why that is, but if you want to ask me, you can. Of course, the discovery of the numerous extremophile metabolisms and habitats, which have greatly expanded the range of watery physical conditions. Extremophiles discoveries have taught us that water is not only necessary, but seemingly perhaps sufficient for life, at least on a planet like ours, that it's remarkably coincident, the range of life and the range of liquid water. And finally, almost finally, I want to get to the outer solar system, that detailed reconnaissance of the outer solar system, beginning with Voyager and continuing with these later missions, has really expanded our notions of habitability, because we've learned about the existence of gravitational habitable zones, which do not depend on proximity to any kind of star, and in fact, who knows, may define the largest amount of habitable real estate in the universe. Finally, more recently, the discovery of a complex methane hydrosphere, or methosphere, on Titan, and a likely subsurface aquifer on Enceladus, along with a rapidly expanding catalog of exoplanets, has stimulated new ideas on the range and detectability of planetary habitability. And we're even thinking a little bit more about life beyond water. It's being taken a little more seriously now because of the methane, liquid methane cycle on Titan, combined with the existence of complex organics and copious energy sources. There are some very clever chemists that are working on this problem and sort of pushing us again to question whether our water bias is intellectually valid or just a parochialism based on the experience and environments of Earth. I wanted to say, I'm almost done, I wanted to say just a couple things about Venus, because I submitted an abstract that was just about Venus that was rejected from this meeting, which is fine. but especially having been shoehorned into a Mars session here, I'm aware of what might be called a little bit of myopia, although it might be a useful myopia. I believe in exploring Mars, and I believe there are good reasons to explore Mars first, although partly we may be searching under the streetlights for our keys, because Mars is certainly much easier to explore. But just a couple quick points about Venus, that its close proximity to Earth and similarity in bulk properties suggests an almost controlled experiment with heliocentric existence in the presence of life as the two main variables. Yet major differences in their evolutionary paths have caused us to reevaluate our models of terrestrial evolution. Certainly, if we want to know the limits of a habitable zone around Alpha Centauri b, which people want to know now, the best way, I would submit, is to send new missions to Venus. And certainly if we want to know the future of life on Earth-like planets around Sun-like stars, we had better send new missions to Venus. I was very encouraged by Jim's chart showing that there are some big Venus missions at least on the chart, if not nearing the launch pad right now. If Curiosity finds signs of life on Mars, in a strange way it will confirm our views of the origin of life. It doesn't really revolutionize scientifically our view, it confirms it. When we find those conglomerates in Gale Crater, we're confirming what we thought, that there was running water there. It's very exciting to find, but it's interesting to me that in a certain sense that if we make that tremendous discovery, it's more a confirmation than a refutation of our current sort of naturalistic worldview about life and what it takes. In conclusion, astrobiology is about the relationship between planets and life. Today, we are more sophisticated about planets than we are about life. We're beginning to learn about the diversity of planets. We know nothing about the diversity of life. In another 50 years, I expect that we will. Thank you.
Thanks so much. About 5 minutes for questions.
That was really great. I wanted to poke at something that you said earlier in your talk that would appear to be at conflict with something that you said later on. You made the observation about life existing at the interface between external and internal heat sources. And yet we think about Europa, it doesn't really have an external, it's internal. And Titan almost the same way. And yet your later statement was these may be the most prevalent habitable zones in the universe. Can you expand on that? And
yeah, certainly. Very good point. I think that when we look around the universe and we try to derive criteria for what might make a habitable environment, we're very susceptible to the danger, or we're in danger of just looking for ourselves out there and for reaching the conclusion that, the Panglossian conclusion, this is the best of all possible worlds. We just have to look for a place with conditions just like this. And it may be true, but it may not be true. So it's interesting to say, well, okay, obviously Earth has a climate conducive to liquid water on the surface, and that's one set of criteria. What else is it about the Earth that's unusual that could also possibly differentiate habitable planets from non-habitable planets? And it is striking the level of ongoing geological and meteorological activity on Earth, and certainly life, the more we learn about life and the way it fits into Earth system science, it takes advantage of that. It's not just a coincidence. So that's really my point, is that, that's something unusual about Earth, and for all we know, it may be true of all habitable planets. And in that sense, I'm intrigued by the fact that Titan shares that. Now, Europa is an interesting case, and maybe is a test of this hypothesis. If all you need is liquid water and organics and energy sources, Europa ought to have life. But in a certain sense, if you sort of, what I'm calling the living worlds hypothesis, if you generalize it to you need ongoing, internally driven geologic activity that is feeding this sort of cyclic exchange of matter and energy that life feeds off of, then I think you could argue that Europa shares those, although maybe that this intersection of two heat engines is specifically relevant for surface life. obviously, I'm still working on the idea. Maybe we should have a beer later and refine this, yeah.
Oh, this is information, you probably know it well. I've had a long relationship with the Museum of Science in Baltimore. I've lectured there many times. And they're opening an exobiology exhibit sponsored by NASA. I'm sure you knew that. That'll be on the 1st of November. I've been invited as a donor, but you'll never guess what I loaned them. They wanted a pristine first edition copy of The War of the Worlds. That's good exobiology, isn't it?
Excellent, excellent. Well, I think it's a great choice. If for no other reason than the first page of The War of the World is one of the finest pieces of Western literature that exists, and even that sort of crappy remake of that movie with what's his name in it, the beginning of it was wonderful because it had the voiceover directly reading from that first page, which is it's worth just watching that scene. Yeah.
Okay, thank you.
I seem to remember there was an instrument on Curiosity that would help characterize the source of methane that's been seen. Have we gotten any recent news from that?
That's a great question. Curiosity should be able to resolve the methane issue. And when I mentioned the recurring existence of wishful thinking in interpretations of data from Mars, I was thinking, for instance, about the publication in the 1960s of in Science magazine of the spectral signature of chlorophyll on Mars, which later turned out to be deuterium in Earth's atmosphere. And it may turn out that these methane observations historically fit into that pantheon of optimistic interpretations. We don't know yet. It's controversial, and there's some very smart people who are very critical of the methane interpretation, and some other very smart people are sure that it's true. And it's exciting that Curiosity has that ability in the SAM instrument to look for very minute quantities of methane. And methane is a leaky substance, and the Curiosity team is large, and there have been some hints that maybe some people know the answer to this question. And I was during Jim Green's talk, I was trying to read his lips very carefully, but nothing has been officially released. But I wouldn't be surprised if sometime this year there was an announcement about that.
Thank you very much. Thanks, David. Great. Our third speaker is Eric Conway, who's a historian at the Jet Propulsion Laboratory. Eric is the author of several books in the history of space technology and aeronautical engineering, including The Technopolitics of Supersonic Transportation, Atmospheric Science at NASA, and a book on blind landings, among other. Last year, Eric won the Davis Prize from the Society for the History of Science for extraordinary writing for the public domain. But I should also note that his work in the history of science and technology and in the history of space exploration has been both foundational and extremely influential. So Eric is currently working on a history of Mars exploration since the 1970s, and he'll be speaking to us today about Mars sample return.
First, I have to thank the previous speakers today. You've made my problem of getting through this talk on time much easier because I don't have to cover some programmatic stuff that's essential to the story I actually want to tell, which is about really engineering for Mars sample return. Now, you've all heard this mentioned many times. This is the Mars Science Laboratory / Curiosity landing. But the story you probably don't know is that this architecture was the loser of a sample return study done in 2000 around JPL, and then one again a few years later. And that's the story I want to tell. There are samples of Mars on Earth. Most audiences I give this talk to don't realize that. We have these meteorites that were collected from Antarctica. This is the famous one from 1996 that was supposed to have been found to have signatures of life on it. The reason I bring it up is to get across the idea that what scientists want is not just any old sample of Mars. What they want is to pick them. And that's important, because you heard from Rich Zurek how frustrating the Viking missions were to some scientists because they could see some wonderful rocks that they wanted to reach out and grab and test and couldn't. They couldn't get to them. So when this strategy for exploration of the inner planets is published by the Complex Committee in 1978, it's contains a discussion of Mars sample return that favors doing it with some sort of rover, either a short-range rover that could go maybe only a few meters, but what they make clear is what they really wanted was a long-range one that might cover hundreds of kilometers. Now, the threads of my story are design and engineering in support of science. There's a second thread of competition for funds I'll get to at the end. And ultimately, I want to leave you with the thought that you've already heard today, that NASA has this dual self-image, sometimes I call it schizophrenia, as a scientific agency and also the agency that's an agent of human expansion into the solar system. Now, that complex study led to a set of studies at JPL that I'm not going to talk about. There are actually 4 separate sets of sample return studies, major ones anyways, that I talk about in the full length of this paper. I can't do them all in 20 minutes, so I'm going to do 2. I'm going to skip merrily over this period of time and get on to the second act of the sample return in the faster, better, cheaper era during the 1990s. One of the other speakers already introduced one of my favorite poster boys, the Mars Observer mission. This has become legendary in the planetary science community for being overcost and then not returning anything. One corrective to a previous speaker is that the primary overrun came from the launch delay of 26 months, not from the instruments. They were the second largest piece of the overrun. Either way, we got nothing essentially out of this, except the value of the systems engineering, which contributed to a number of missions later on, once Dan Golden and Wes Huntress have reformulated the idea of A, faster, better, cheaper, and then B, the idea of a Mars program. This is the Mars program that came out of their work in the early 1990s, and I show this because sample return over here, oh, this is very weak, unfortunately, appears. The idea of the Surveyor program, it was called, is there would be an orbiter and lander, 2 missions sent every 26 months, every launch period to Mars. The first pair would be an orbiter and a lander. The second pair, again, an orbiter and a lander going in 2001. And then in 2003, you would get the beginning of the sample return campaign. This was challenging technologically because the missions were supposed to be implemented by contract. They were also supposed to be competed except for sample return, which meant they didn't lead up to a technologically coherent mission set. In other words, they didn't build towards sample return from the standpoint of the engineers that had to work on these things. There we go. At the same time, outside the Mars program, this of course is Mars Pathfinder, which was done under the Discovery program, was set up to demonstrate low-cost Mars landings. This is a famous picture of the Sojourner rover starting to deliver the technical promise of the ability to reach out and get samples from distant areas. The Mars Pathfinder mission, of course, was enormously popular with the general public, so it validated the idea of having a Mars program. It also validated the idea of faster, better, cheaper. The lander cost about $150 million. The project overall, $310 million, which is about 1/10 of what the nation spent on Viking. It was supposed to be followed by this mission, the Mars Polar Lander. JPL selected as its contract partner Lockheed. The Polar Lander was to be of their design. This was a pulsed jet lander, not a throttleable liquid the way Viking had been done. The idea was to land near the Martian North Pole, take samples, and test of more polar, but not necessarily on ice samples. This mission was the contract value for this project was $120 million. The project budget overall was around a bit over $250 million. So NASA was asking JPL to deliver 2 spacecraft for less than it spent on 1 in Mars Pathfinder. And the sample return architecture was then to be based on the Lockheed lander. The sample return architecture was a 3-way effort of JPL, Lockheed in Denver, really, and the French space agency, CNES. It was to start off in 2003 with either a Delta or Atlas launch, putting up the Lockheed lander with a small Sojourner-derived, but larger than Sojourner, more of an Athena-sized rover of around 120 kilograms that would go out and collect samples and then shoot them off into space. You can barely see it. You'll see this better on the next diagram, into low Mars orbit. In 2005, an Ariane 5 with 2 more spacecraft, another lander, and a French-built orbiter would be sent to Mars as well, collect samples, shoot them into orbit, and then the orbiter would collect them and send them back to Earth via an Earth return vehicle. This is the scaled-up Lockheed sample return lander. I pulled this out of a presentation by Ed Euler, who was the Lockheed program manager for it, presented at one of the AAA meetings back in 2000. in 99. This is the landed configuration. You can see the Mars ascent vehicle that's to shoot it into orbit here, the rover and the platform it's supposed to come down. Drill envelope for in case the rover didn't work or failed before coming back to the lander. It had the ability to just grab a sample from where it landed and send that back. As a technical problem, this lander was substantial because it had to be scaled up considerably. The Polar lander was supposed to have a mass of about 290 kilograms. This thing had to be a bit over 1,000. Anytime you scale up a piece of hardware to that degree, you have to do a lot of redesign work. And this project is set up at JPL. The engineers begin to realize that they have technical issues with these legs because they're a bit fragile, because the launch vehicle shrouds would not allow a long enough leg to give any substantial ground clearance. So then you have the problem of, well, they're going to flex during impact when it hits the surface. How much space can we have for that? They ran into troubles with the load pass that would carry this down to the launch vehicle, and so on. And they began to question whether this design was actually sound. They also began to question whether they were really going to have enough money under the $200 million a year budget that the Surveyor project could give them. But it's not in the end the money that gets them into deep trouble. It's the loss of the Polar lander. When the Polar lander is lost, it's lost without returning any telemetry at all. So there is a study of its failure. They came to a set of conclusions that it was probably a touchdown flag that was misset. JPL, that's almost, I think, universally understood to be unlikely. It failed for other reasons that were found by a project later on called Mars Phoenix when they took the O1 lander hardware to rework. But at the time, no one knew that. All they knew is that the Lockheed lander had failed and they didn't know why. And that ended this sample return effort because it was based fundamentally on the success of the Polar lander. Act 3. So I've now said that around JPL, the sample return idea, the architecture, was already in trouble, and the laboratory sets up a couple of design teams to revisit this as the sample return project itself is being shut down. It starts out in the leadership of Brian Muirhead, who had been the Pathfinder project manager and had a number of the Pathfinder veterans on these teams. The idea of the bubble team study initially was to review each element of the architecture individually. Muirhead's team reviewed the lander. They then morphed into a different set of studies, but essentially the same people under another program manager by the name of Jim Graff, known as the Large Lander Study. And this is where they begin to reformulate a different architecture for sample return. This is the way the engineers like to tell their story. This is the Polar lander. The Polar lander has a series of review boards that try to examine its failure. This idea of robust rover egress here at the bottom for sample return was never addressed because they'd begun thinking about this egress problem, and that leads them into this next phase, which will eventually be called the Mars Smart Lander. Now, in this Bubblehead team, they come up with a variety of different potential architectures, and this slide, one of the engineers built, and I grabbed out of the presentation, shows the evolution of their thinking from this tripod lander to what becomes the baseline, or one of the baselines from this study, and that is the idea of a pallet lander. The pallet lander is an idea from the 1960s. The idea is a crushable substructure. I have 10 minutes. Okay, thanks, Janet. I'm doing pretty good then. The idea is you have a crushable substructure that means you don't have a very large ground clearance once the thing is sitting on the ground, and that's desirable from the standpoint of getting a big rover off the deck. If you have it sitting very high standing, which on a leg lander you want for rock avoidance, as the rover moves across the surface of the thing, the whole spacecraft will try to tip, and if you are unfortunate and either landed on a slope or on a big rock, you can flip the whole darn thing over. This pallet lander is a little more immune to this. Its drawback is that the fuel tanks are down here on the bottom, and the structure has to protect those because the fuel we use, hydrazine, is both toxic and corrosive, and we don't want it all over the guts of the lander. So that's one idea they come up with. Second idea, airbag system. We've already seen the use of airbags on Mars Pathfinder. Why not continue with that success? Except in this case, because it's a much larger lander, again, you're trying to land 1,000 kilograms, they decided they needed more controllability. And here's the idea, is to use a throttleable liquid descent stage to lower the lander down more gently than Pathfinder had, but they still thought they needed these airbags to protect it towards terminal descent. At the end, again, you see the The descent stage will fly away at the end and crash. The advantage of that is you don't have to protect the fuel tanks because you don't care what happens to the descent stage after it hits the ground. There are a number of advantages and disadvantages. The airbags provided righting ability, a disadvantage that they didn't quite realize very thoroughly yet because, is how to get heat out of the spacecraft in cruise. These airbags are insulators. The Aero shell will be an insulator, and this is a particularly big problem if NASA decides to use an RTG power source because there's much more heat to be dissipated through all these layers of insulation while it's in flight to Mars. So advantages, descent stage never has to be shut off. The propulsion hardware doesn't have to be protected. Better velocity control. Disadvantages, interface complexity. How do you get the rover off? And self-righting. So someone at this meeting, I've interviewed 6 people, all 6 people in the room, no one will take credit for this or assign blame. And by the way, while I've presented this as kind of a JPL story, the reality is a very senior Lockheed engineer by the name of Steve Jolly was in this as well, and I've interviewed him too. Someone comes up with the idea of, why we don't just dispense with the darn airbags? And the reason they decide they can't yet is they can't answer this problem that's illustrated by. That's what's known as a controllability problem. They didn't understand an answer to the question is, what happens if the rover starts to swing in the wind on its way down to the surface? Can any reasonable control system handle that? And the answer actually was yes, but they didn't know it, because the people in the room were mostly mechanical engineers, a systems engineer, and a program manager. They weren't aeronautical engineers, and they certainly weren't guidance and control people. So they shelved this idea and baselined the other 2 to go forward into the next set of studies. In fact, the favored sample that came out of this was the Pallet lander. And here you see a later slide from an early phase of what becomes known as the Mars Smart Lander and then the Science Laboratory. Planning a new Mars program. That's going on at the engineering level, while Firuz Naderi and Scott Hubbard and some others are trying to plan a new program to replace the now dead Surveyor program. At JPL, a physicist by the name of Mark Adler proposed this mission, the Mars Mobile Pathfinder, that actually very quickly floats to the top. It's proposed first in May and finally approved as the Mars Exploration Rover mission in August of 2000. I don't know how they managed to do it, but Mark's folks forgot to put the airbags on. But that goes forward and becomes the short-range solution of what do we do next for Mars. Longer term, they create this program. Again, we have the Mars Exploration Rovers down here, and now we have this thing called the Mars Smart Lander. The Smart Lander is that Pallet lander you saw before. Its initial purpose was simply to demonstrate that you can land a very large payload, this 1,000-kilogram thing for sample return, on the surface safely. They didn't yet conceive it, because again, it's largely engineers, as a high science return mission. And then following the Smart Lander proving that we finally do sample return in 2011. Also on this, you see the Mars Reconnaissance Orbiter. That mission has an engineering purpose. I'm sure you've all heard about its scientific purpose, but it's important to illuminate one of the questions about how to land more safely on Mars. At JPL, there's been a long-standing conflict between the advanced technology sections and the flight sections over how to make for a safer landing. There's an active hazard avoidance group at the lab who wants the spacecraft to look down, see what's going on, figure out for itself what to do. And another faction at the lab who thinks that's a horrible, awful idea, because our rules require every possible decision that the lander can make to be tested. And as the number of options increase and the Mars surface is complicated, as you heard from Richard, the option space for its selection becomes infinite and your test program becomes enormous. So the MRO that comes out of this has the engineering purpose, and that's the large camera that's to do this, is to photograph the surface at such high resolution that they will be able to find places that simply don't have any hazards to worry about, and thus this hazard problem is solved. Whither the Smart Lander? So I said that the Pallet lander became the baseline for the Smart Lander program. This is one of the test models of Tom Rellini, the engineer assigned to figure out this Pallet thing. Very quickly, though, the Smart Lander ceases to be a technology development program and becomes a high science return mission. A science definition team had been put together. When they concluded, they came out with an argument for making the Smart Lander the capstone scientific mission for the decade. which meant an expansion of the budget in the project from the $750 million Smartlander to the $1.5 billion science laboratory, and the name was changed too. At the same time, well, a little bit after this happens, the engineers revisit this selection of the palette. They do it because they learned a lot during the Mars Exploration Rover mission. One thing they learned is that this control problem is not a problem. There are solutions for it. They could get them, they could essentially buy them. They'd been solved by other organizations. They discovered this in all the testing program that they did for MER that they had not done very much of for Pathfinder. They also become much more afraid of this egress problem. The picture over here of one of the MER rover prototypes with the lander hung up on a rock mortified them, because very often they had these rovers simply flop, which would have been a very expensive and embarrassing mission failure on the day of landing. So this egress challenge rose in their minds to be a much worse problem than this controllability problem. So at a design review in 2004, they revisit this trade space, as they call it, and eventually come back to the conclusion that they had rejected before, that they should just get rid of the bloody airbags and the lander and land straight on the wheels. The demise of sample return. I commented earlier today, and I'm probably going to run out of time. NASA has tried repeatedly to develop a new human launch vehicle, and it has not succeeded at it. Those are 4. Here's the 5th one in the vision for space exploration. It was called Ares. You probably all remember it because it's not that long ago. It was supposed to be the basis for sending humans back to Mars, but it was not. It was supposed to be funded by an increase in the NASA budget of about $3 billion per year, plus the shutdown of the shuttle, which occurs after this point. That $3 billion a year never materialized. NASA actually got about $1.5 billion, and what happened around headquarters is that they then went looking around for donations from the other programs to finish Constellation. The Mars program was told in May 2005 that its contribution to Constellation would be about $3 billion over the next 5 years, which looks like this. This was the budget they were expecting to get, the blue line, and this is the budget they were going to get, well, for a few years. That actually was cut even worse. So the sample return went away. As one Aviation Week reporter, a cut of this magnitude pushed sample return off the table and onto the floor. So I probably don't have much time for conclusions or ruminations, but I think I'd rather just let you ask me questions.
I can start with one by asking you to.
So I mentioned the schizophrenia of NASA, that it's both a scientific agency doing sciences across many different disciplines, and an agency that sees as its mission the human colonization of the solar system, I think. And as you've seen, not just in my talk, but in some of the other talks, these two things sometimes work together pretty well, and other times they raid each other's budgets. And so there's a constant conflict around NASA that I often have to explain to audiences. The Science Directorate, in my view, plays sort of a round-robin game, since it never gets as much money for all its ambitions. It feeds some things well for a while and starves others, and that circle always goes around. And so one of my ruminations is it ever going to be possible to do sample return given how much it's going to cost? Because you can't sustain a funding profile in the Science Directorate for more than 3 or 4 years, and that's not enough time to get sample return done on the amount of peak budget that's available. So that's one of my questions. And I can't answer it because, of course, as a historian, I only deal with the past. It's Jim Green's job to deal with the future. But I wonder about that. So that's one of my ruminations. Another, one reason I picked this subject and Mars exploration overall from an engineering perspective is I'm interested in the way engineers take lessons from one project forward to the next one. If I had more time, I would tell you that the folks who were on this bubble team study were almost all Pathfinder people, except for Steve Jolly from Lockheed, who is involved with the Global Surveyor and Polar Lander missions to some degree. And so their experience, their reason they had that bubble team study came from the Pathfinder gang's experience, and then after they all get drafted into the Mars Exploration Rover mission, it gets reinformed by that. That was suggested in here, but not made terribly clear because I'm in enough of a hurry to get off the stage. Oh, and I guess I have a question.
Nobody I decided to be, just to ask a question. Are you going to return sample from some specific landing site, or just to collect several samples, from some area around the landing site with a capable rover equipped with manipulator and possibly even drilling in order just to return deep-seated, probes?
Oh, I guess the answer is that Jim Green has to answer that question. What the scientists clearly want the most is a long-range rover that can go hundreds of kilometers, collect many samples from many different terrains. If they can figure out how to do it, a drill that will actually pull them up. I think there's a drill on Curiosity, but I don't know what its capability is because I only study the past. So that's clearly what they want. What they're going to get is whatever the science director can afford, which might be nothing more than the grab sampling. I just don't know. Again, I deal with the past, not the future. But I think that's your trade space. There's what the scientist wants, so part of my story is ambition, and then there's what we're actually able to get out of Congress to pay for. And that's the other end of the spectrum.
Heidi Hamill from Aura. I can think of an astrophysics example where it has benefited from its interaction with human spaceflight program, and that would be Hubble, which we serviced 1,000 times. That's an exaggeration, but you get the idea. But I'm struggling to 5 actually, right? There was one was twice. Well, but I'm struggling to think of ones that where the planetary science community benefited from interactions with the human spaceflight program. Can you think of some or give some examples?
To a small degree, Mars 01 project had some instruments that were supposed to contribute to the human program. The reason I'm not willing to say that's an unalloyed good is that the human program ultimately wasn't willing to pay for them. And folks at headquarters had to go begging around Congress to get some extra money in order to actually put them on the vehicles. And then, of course, the lander was canceled. So only I think it's the Marie instrument on the Odyssey orbiter, the 2001 orbiter, actually flies. And that's clearly a contribution to understanding Mars well enough to send people there. But I'm sure it's not quite as great an example as Hubble is, which, you're right, clearly benefited from being shuttle serviceable. Because the planetary stuff, because we send it off and don't get it back, there hasn't been quite that strength of interaction, to my knowledge. Greg? Yeah. Yeah, that's right. So he's talking about the Surveyor lander program, for which there hasn't been a history written, and I actually came out here early to dig through some of the records from that, because that's the next project I want, or program really, that I want to write about is historically. Else?
Fabulous. So we've heard about the missions, the science, the engineering, and now let's take a turn towards headquarters and those people behind the scenes. So Harry Lambright is Professor of Public Administration and International Affairs and Political Science at the Maxwell School of Syracuse University. He's authored many works, including a biography of James Webb called Powering Apollo, and is editor of Space Policy in the 21st Century. Harry is also a fellow of the American Association for the Advancement of Science and the National Academy of Public Administration.
Well, I wish I had some pretty pictures of men, at least, but I don't. We have, 4 administrators sitting behind desks in suits. I don't think would go over very well with this audience. With these, so So anyway, I tried it out on a female graduate student, and she said, "Don't do it, whatever you do." So anyway, I'm going to talk about people. You said, are individuals important? Yes, of course they are, but are NASA administrators important? It's an interesting question. I had occasion to interview a scientist at JPL named Dan McLeese, who was told me about experience he had with Dan Golden after the meteorite situation in 1996. Dan Golden was very excited about the meteorite, and he wanted to know from the scientists, what's the next step? What's the next step? What do we do next? And they said, well, the only way you're going to find out if you're going to have life is Mars sample return. He said, great, let's do it now. And he kept pressing them for given particular years. And all of them were, the scientists said, we can't just send something up there. We've got to know where to go. And they reminded him of Viking, where the answer had come out and it had hurt the program. So we've got to be systematic, incremental, comprehensive, et cetera, et cetera, et cetera. He said, fine, okay, do what's right by science, but remember, the pace will be determined by politics. True. Now, how does, it seems to me the role of the science, the role of the administrator, the NASA administrator, is somehow to sort of cross those boundaries between the worlds of science and technology and NASA and the worlds of politics. In the vernacular of political science, the NASA administrator falls into a class of people that are called political executives. What that means essentially is they are executives. That is, they run organizations. They have executive jobs. They deal with personnel. They deal with budgets. They deal with organizations and reorganizations. But they're politicians. That is to say, they are appointed by the president and confirmed by the Senate and are expected to play advocacy roles on behalf of their agencies. So they have inside jobs and they have outside jobs. And they have to do them both to be effective as administrators. And this has always been the case, and some are more effective than others. It's to have the kind of skills that it takes to be effective in both of those roles and to combine them in one man. It's rare. There aren't really many people at NASA or other places who have had the gifts that go with playing that kind of total role. The closest you come at NASA was James Webb, and there is a fascinating story about Webb and playing that role, and it's coming out with the Kennedy tapes, when in the early days of Apollo, the President, Kennedy, was dealing with a dispute, a power struggle within NASA between the head of the human spaceflight program, who wanted all the money for Apollo, and Webb, who wanted some of the money to go to the science program that he was beginning to build up. And it came to Kennedy at the end of the day to make the decision. And Kennedy, and this is something that bothers a lot of people, basically said, I don't really care that much about space or science. I care about beating the Russians. And Webb had to make the point that Apollo was a means to an end, and the end was preeminence, leadership. And he said, science is also that way. Science is a means to an end, the end being preeminence, not Apollo for its own sake. And Kennedy said, well, I want you to, I'm not sure we're on the same wavelength. You go back and write me a memo and explain what you're talking about. And he did that, and Webb never heard back. And as a result, the head of the Apollo program was fired, and Webb continued. He bridged the gap. He explained to the president why science was important. And science continues, and we're here today. Now, there aren't many people who can do that. I found actually one person in Washington today who seems to have those skills. If you want to see what it takes, take a look at Francis Collins. Francis Collins was head of the Genome Project, and now he's head of NIH. And he seems to have those unusual combination of skills. But they're rare, and there aren't many. And there have been that many in NASA history who have had the blending that it takes to be both a solid manager and a solid politician at the same time, because most people don't have it. In any event, what I'm going to talk about are four guys as they relate to the Mars program. Now, in connection, when you're dealing with a NASA administrator, remember you're dealing with the equivalent of a CEO of a corporation or the president of a university. They have many programs. Mars is just one of them. And all NASA administrators have focused mainly on the human spaceflight program because that's where the money is. And that's where most of the political issues are. So Mars, so the question is how do NASA administrators deal with Mars? Well, essentially they don't deal with it very much, but they do deal with it once in a while. And when they deal with it, usually it's because they're dealing with the biggest decisions. The biggest decisions ultimately come up to the desk of the administrator. And these are decisions like, as in a human life, they're the decisions of a program getting born, a program being significantly reoriented, or a program being terminated, or being in danger of being terminated. And that's when NASA administrators get involved with science and get involved with Mars in particular. So we'll start with Dan Goldin. Dan Goldin, was probably the most controversial NASA administrator in history. You can get a different view of Dan Goldin depending on whether you're looking at Dan Goldin and the shuttle program, or the space station program, or the Mars program. When it comes to the Mars program, I think Dan Goldin looks pretty good. Now, why do I say that? Well, I say that is that it was a passion for him. He was genuinely interested in it. We all know that when you're dealing with leaders, it's a mix of personality and situation. We all know that. Now, the personality of Dan Goldin was dynamic, intense, and intimidating for anyone who ever met him. My first time I ever met him, I thought he was going to explode on me. You got an hour, he told me. You got an hour. Boy, I jumped up and I started asking questions real fast. But that was Dan Goldin, and that was my introduction to him. Next, I'm so full of anecdotes on Dan Goldin. As I was leaving, he grabbed me by the lapels. And you know what's wrong with NASA? NASA, young guys don't work hard enough. I was on an airplane at 6 in the morning, and my guys were all sleeping while I was working hard. That was Dan Goldin. Anyway, if any of you know him, you know this is Dan Goldin. Intense man, terribly intense, and he loved Mars. He spent most of his time on the space station and the human space program, human space flight program. But what he loved was Mars, and it was a love affair. If you recall, when he was hired back in 1992, Bush 1 had this Moon Mars program. It didn't go anywhere, but that's one of the reasons Goldin took the job. He thought he was going to run this Moon Mars program. It was a human program. He found out very quickly it wasn't going anywhere, but he still wanted to do Mars. He still wanted to do Mars. And so he looked at Mars as he looked at the question about human and unmanned. He looked at Mars from the standpoint of precursory to manned space. If I can't get a manned program, I can do what we did in the Moon program, which have a precursory program. So that's how he saw it. That's how a lot of administrators see it, incidentally, because they come at it from the human space program. Now, the big decision he made came after Mars Observer. He made a number of decisions, but I'm going to deal just with what I think are the biggest ones. First decision he made had to do with was after Mars Observer went down, and essentially, he didn't want it to go. He spent time talking to his science administrator, who was Wesley Huntress, I think is sitting here, and he talked to Carl Sagan. Oh no, 10 minutes. I've only gotten to start a Goldin. All right, so here we go. All right, real quick. Basically, what happened is essentially these decisions are made by 100 people, but the guy who's in charge at the top has to sign off on them, has to make the decision, and then he has to sell them to the political community. Basically, the decision is made. We're going programmatic. not just a one-shot affair, Mars, like Mars Observer, but a program with many missions that would be integrated and coordinated. And it was sold as such. Wesley Huntress, very important in this whole story. But the deal that was made is OMB, which they don't like. OMB, Congress doesn't like these programs. They'd like to keep them separate. They have more power that way. But if you let us have a program, it'll be faster, better, cheaper. Faster, better, cheaper is the way you're selling it. It'll cost you less over a period of years. So it was accepted, program gets started. Next decision, reorientation, is with the moon rock, with the Mars rock. And essentially this is the idea of speeding up the Mars sample return as fast as we can. Faster, better, cheaper. Even faster, better, cheaper applied to Mars. Last decision, problems with faster, better, cheaper. 2 probes go down. What are we going to do? He says to his NASA, his AA, I guess AA at that point, that we got to save the Mars program. He brings in Mr. Hubbard from California, and he tells, reinvent the program. Give me another program that isn't faster, better. I don't think he used those words, but I think I want it to be more realistic. His last decision was essentially Spirit and Opportunity. I am told by everybody that the decision to have 2 is his decision, and that goes way against faster, better, cheaper. So how are you going to pay for it? Mars is important. He taxed other divisions of NASA to pay for Spirit and Opportunity. And then he goes. And so you have the next one, and he is Sean O'Keefe. I know him well. He comes from my place. He is a budget man. That's number 2 in the budget. He's hired to deal with the space station cost overrun, and then he has to deal with the crisis of the Columbia going down. Out of that comes the Moon-Mars decision of Bush 2, and he says, well, again, Mars is precursory to this human mission, and I am going to enlarge the budget of the Mars program. Priority, he comes from OMB. His view of life is it's better to have priorities and do something well than do a bunch of things not so well. And so he says, I'm going to put money into Mars, but money's going to come from human space flight as well as from the science division, and it's going to grow to the billion-dollar class over a period of time. He goes, O'Keefe comes in. O'Keefe deals with the backlash from all the other scientists who say, priority doesn't mean balance. We want balance, not priority. So I think Griffin is so interested in constellation, he doesn't want to deal with the scientific community. Well, you can tell about that, Mr. Huntress. But he doesn't want to deal with the scientists. He wants to deal with constellation. And he says, you science administrators, you worry about it. I'll give you money, leave me alone. I want to deal with constellation. So basically, that's the story with Griffin until essentially he hires a science administrator named Stern, who gets him in trouble with the scientific community and JPL. Alan Stern is convinced there's a cabal between JPL and the scientific community to create this monster called Mars Science Laboratory, which is going to cost billions of dollars, and he points to a National Academy of Sciences study, a decadal study, that says it's going to cost X number of dollars, which is far fewer. So how did it go from A to Z? And obviously, you guys down at JPL and the community must be doing something wrong, and he's going to be tough, and he's real tough. And Griffin says, we got to keep the Mars Science Laboratory going, get the money to pay for it. He looks at Spirit and Opportunity, and he's going to cut Spirit and Opportunity. He doesn't tell Griffin that he's going to cut Spirit and Opportunity. There's a huge backlash from that. Griffin says, you didn't tell me. That's too bad. Bye-bye. And that's the end of Stern. And so he brings in brings Weiler back. Weiler is very, very, very canny, bureaucratic politician. And Weiler basically is the man behind looks at the situation, 5 minutes, looks at the situation and says, we've got to have a delay in this decision. Now, Mr. Green said a delay decision is a big deal. It's a big decision. You don't just delay a mission 2 years and relax. It's a big decision. Stern had gone to Griffin to try to get a delay in the Mars Science Laboratory. He was going to delay it and then put a cash on it to start Mars sample return via Mars Science Laboratory, but he needed a delay to do that. He didn't get his delay from Griffin. Weiler gets the delay. And if anybody wants a real textbook study of how to do things right and how to do things wrong in a decision-making process, study the decision-making process of Stern and the decision-making process of Weiler and how they got the boss to give them the answer they wanted. Because Weiler got the answer he wanted, which is delay, the decision to delay. The decision to delay was a very important decision, probably the most important Mars decision that Griffin made. Griffin goes, and so we got another administrator, and this is now we have Bolden. Now Bolden is our present administrator, and the story is not finished on Bolden. Bolden is interesting because essentially he didn't really want the job. He said that, and he didn't want the job because he had had a job under Golden back in the early 90s and found that dealing with the politics of the job was dreadful. Couldn't stand it. And but he was a good soldier. He's a military guy, and so he said when Obama asked him to take the job, he couldn't say no. Having taken the job, now he has to run NASA, and he asked for the commander-in-chief to give him his marching orders. But as you know, he didn't get any marching orders for a long while. It wasn't until the next year, 2010, that a budget came out, and the budget said we're going to cancel Constellation. Now, Bolden had had very little influence in that decision. And the critical question you want to ask about a leader is, does he have influence, and does he use it on behalf of Mars? That decision, that rollout decision, was dreadful. Bolden calls it a disaster. It was a disaster for NASA, and it was a disaster for him personally, because he hadn't had that much control over it, and the Congress says, why should we talk to you? We should be talking to the OMB or somebody like that who really makes decisions around here. And the consequence, it hurt his influence. And so Bolden becomes caught between this toxic thing that he desperately didn't want to be part of Washington, which is the Congress and the President fighting over a program called Constellation, which has been killed, and what are we going to replace it with? And in the end of the day, finally, after months and months and months, Congress makes a decision, which forces on the President, which we're going to have a major manned space program, which the space, what's this called? The space, whatever it is, it's the rockets, big rockets, heavy lift, and we're going to have Orion, 2 minutes to go. And, but they're not going to give you any more money. So all of a sudden, you've got a situation of being an administrator in which you've got this massive new manned program. You've got the Mars program, which you are very supportive of, and I'll get back to it in a minute, because essentially while all this is going on, this big politics stuff is going on. What is going on at the science level, Weiler level, is a negotiation between Weiler and his counterpart in England to have Mars sample return via this ExoMars effort with Europe. So this is going on at that level, but this other stuff is going on at another level, which is all about manned space and all about money, and finally they come together when you're dealing with the budget between Thanksgiving and Christmas of last year. When you're dealing with the final budget decisions, NASA has people in Paris negotiating with Europe over ExoMars. Bolden is talking to Dordain, his counterpart over there, about whether or not we can really go ahead with this. This is 3 years of negotiation that's been going on. At the same time, he's talking to the Budget Bureau, the Office of Management Budget, and the Office of Management Budget says, look, you've got no money for James Webb Space Telescope. It's gone up to $8.7 billion. Where are you going to get the money for that? He says, they say to him, make a decision. Webb versus Mars. What do you want? You can't have two huge flagship programs. It's not the decision. And so Bolden says, well, the truth of the matter is, Bolden makes a decision, but it's not his decision. It's forced on him by the OMB, and is forced on the OMB by the political people who have already decided that James Webb will survive, one way or another, and we'll take the money from somewhere else. So, what is the moral of the story? The moral of the story is that if you're asking the question, do NASA administrators matter? Yeah, they matter. Do they have influence? Not all of them. And if they have influence, they use it for Mars when they can.
Are there any questions for Harry?
Lucas from NASA Ames. Excuse me, my question is whether a NASA administrator will ever be able to set a rational strategic direction for the agency. Should we be looking at another type of organization to do that, like a committee? And I've been thinking about that since this morning when Dwayne Day was talking about the SSB and how that absorbs some of the functions of the NACA. Jim Green is saying that the decadal surveys work very well in setting a strategic direction and giving everything that an administrator has to balance. Should strategic direction be coming from a different area that he could then implement?
I think that the problem of any administrator, the problem any administrator has dealing with the issue of a rational program is that any administrator isn't around that long. The typical administrator is around 4 years, maybe 5 years. Golden was the exception, being 9.5. That's rare. So the best you can do is to have the community come up with a rational program, have the program office, the people who are career civil servants, buy in to that rational program, and then you try to make sure the administrator is on your side and that he's good enough to sell it to the political community. Essentially, Mars exploration is like a marathon race. It's going on over years, decades, really. And the administrator comes in and vectors into that off and on. So the more you can have you'll never get rationality. You get what is called muddling through. Muddling through, and that's the best you're going to do. Muddling through is the best you're going to do. That's pretty good.
Panelists to come up and speak. We can take about 5 minutes for a question. Thanks. So we've had a variety of fantastic perspectives of Mars exploration. Let's open the floor for questions.
Hi, I'm hiding behind the column here. Richard Burke, I'm Jim Burke's son. A question back to science. Several speakers have alluded to liquid water being the gold standard for habitability. Wondering about organisms in Antarctica that have no liquid water, and if there's any addition to this discussion anybody could make on that basis.
Well, it's a great question. One of the things that the extremophile revolution, if we can call it that, or the march of discoveries of ever increasing extreme conditions that life can inhabit on Earth, what they all do have in common is their utilization of liquid water. But what's remarkable, and you've alluded to this in the situation of Antarctica, is the way in which life has the ability to really push that boundary. So even in situations where it's only sort of true there's liquid water, and these cryptoendolithic organisms that are living inside of frozen rocks in Antarctica, but somehow using sunlight in the top layers of those rocks to slightly warm themselves above the freezing point, or places where they're using the salinity to push down below what would seem to be the cold limit, but they're using various natural antifreezes. So I don't think it's literally true that we've found life that does not use liquid water, but it is remarkable the extent to which you know, the literal interpretation of what we mean by liquid, both on the cold and hot and saline and acidic boundaries, have been pushed by life. And it really shows us, as I said before, that life seems to be not just necessary, but almost, that water seems to be not just necessary, but almost sufficient for life. So those examples kind of contribute to that sense that, at least for our kind of life, that liquid water in all its manifestations, even if it's just, you know, on the grains between minerals and an otherwise pretty dry and pretty frozen rock, is really the key criterion.
Any further questions? Oh, sorry, answers?
And this really matters for Mars.
I think so.
This really matters for Mars because of the temperature environment of the planet, of just how close and where you might be in terms of getting liquid. And if you get it liquid by making it a brine, then you have other issues with biology. The water activity is really what counts. So it's an important point. I'd like to take just a moment to further answer a question that was asked about why aren't the meteorites the samples of choice. One reason is because you won't get a sample of a sedimentary rock back via a meteorite. It's just not going to happen, and yet those are the very kinds of materials that could really preserve biosignatures of that past life. So it's not just a matter of we don't know where the rocks came from, it's also a matter of we want the right rock, and that's what we've really been trying to look for.
Other questions?
So one of the issues that the Mars program has been dealing with of late is competition. The Decadal Survey obviously recommended the Mars sample return as the primary flagship mission, but the Europa mission was certainly highly considered as well, and I think there was a Uranus mission as well. What do you see as the technical, scientific, or political validities of a Mars mission as opposed to the other missions? Why do you think that Mars should be first, or do you?
What, you're asking a set of Mars?
You're asking a Mars thing.
I truly believe that the issue between, say, Mars and Europa, it's not really a question about which of those goes. The Decadal Survey was pretty clear that, you know, give this a try. If you can't work this out, this is next. Our problem right now is we can't do any flagship class activity with the budgets that we've got going forward. So I think that's the real issue. Solve that one, and then we can get back to arguing the scientific priorities.
Yes, thank you. John Sarkis from the CSIRO in Australia. Just in regards to sample return, everyone agrees it's a desirable mission and so on. However, as I see it, there are potentially very large risks involved in that. So, for example, if the sample contains some microbial life or so on, then returning that to the Earth could be potentially catastrophic because there would be no immunity to it. But also, if we do send people to Mars in the future, then we'll immediately contaminate the place, and therefore, you know, we'll never be quite sure if we do discover life subsequently. Is it indigenous or was it introduced? And so I'd like to hear your opinions on that, you know, about how we could get around those two problems and be confident that if there is life, we're safe from it, and also, you know, that we're confident that it is indigenous to Mars and not introduced.
Well, of course, NASA has a planetary protection program which specifically exists to address those questions. We don't know we don't have a completely clear answer to how serious those concerns are. My own personal view, likely to be infected by Martian organisms, even if they do exist, because if you look at Earth, the evolution of parasites and of dangerous microbes and their host and target organisms is very closely coupled together. And so it's I think less likely that we would suffer an infestation by some kind of organism that had really had a separate evolution. But of course, we don't know that, and because of the existential risks involved in being wrong, the responsible thing to do is to have a planetary protection program, and in my view, we have an adequate program to guard against that. But, you know, it's worth asking, and we continually review that question, and we ought to keep doing it as we learn more about Mars and about life.
There's one more question from the audience.
I actually wanted to offer an observation which is sparked by the question of Mars versus Europa. And it's a personal observation. Over the past few weeks, I've sat in on briefings on two major studies that NASA initiated in response to the proposed budget cuts. Orlando Figueroa led a group called the Mars Program Planning Group, MPPG, and the Europa folks, their science definition team, under Jim Green's direction, went back and did a major study. And both of those groups bit the bullet, and they completely rescoped the missions that had been part of the decadal survey, and maintained a substantial amount of the science that both of them had in the decadal survey, which makes them still high priority, and yet they've managed to reduce the cost by a factor of 2 or more. And the cost has been validated by an independent group of people, the same group that did the validation of the decadal survey missions to begin with. The irony to me is that if the budget were still at 1.5, it wouldn't be either or. We could do them both. We could be standing on the, on the threshold of a phenomenal era where we can actually explore this question of habitability on two fronts at the same time.
Well, we had the benefit over this last decade of both a very vigorous Outer Planets program and a very vigorous Mars program. And to argue scientifically that, we should have just had one, it's certainly hard to do that given all the discoveries in both of those areas. Just to finish the point about sample return, if you have a sample return is one way of knowing what the environment is before the humans step down on it, and whether or not there are certain dangers that they might encounter in that environment. And planetary protection is the thing that is going to keep us safe in the meantime of that first step by a robotic program.
All right. Thank you very much. And let's take a minute to thank all of our speakers. And I've been told you get 10 minutes and to see you back here at 25 past.